Hello again, Codebreakers. Welcome back to another episode of the NSA Codebreaker Challenge 2019. Now we're going to be getting down to the very last task number 7. And if you've watched the previous videos, then you'll see how we got to this point by kind of methodically picking apart the Terror Time app that these terrorists are using. This last exploit, up until this point, we haven't been able to actually decrypt any of the past messages. But in this case, we've actually got a briefing here that describes how the arrested terrorist from Task 3 has revealed that he actually had some part in developing this application. And he hid a subtle vulnerability in the app in order to have kind of an insurance policy. So we can see that they have a download here for the Terror Time key generator. And this is supposed to be an executable version of the library that is included with the app. So whenever a new user registers an account, it uses some algorithm to create a new public and private key for them. And so we're going to be reverse engineering this and discovering what that vulnerability is so that then we can go back and crack the public keys of these other users. So the first step is that we need to just go ahead and pull this up I'm just using the free version of IDA here, and we can start to kind of examine this and see what it is that we're going to be expecting. Now, there are a couple of different common attacks of RSA that you can look at first, and some of the things that I tried first when doing this challenge. One of them is that possibly there could be some method here that the key generator program is seeded with the value of the username that it's going to be generating a key for. So maybe it could be deterministic in some way where we'd be able to tell exactly what value was going to come out. Another attack that we could have would be if the key generator is not random enough. It could be generating prime numbers that are predictable in some way. So there's a chance that if we were to use this keygen program, then we could go and just continuously generate tons and tons of keys and see if eventually one of them shared a factor with the target key of one of our Terror Time users. Because if you recall how RSA keys work, the RSA public key modulus is the product of two large prime numbers P and Q. So we can check if there's a greatest common divisor greater than 1 using a simple Euclidean algorithm that will run very quickly. And we can pretty efficiently determine if any of the public keys that are generated match the factors, or at least one factor, of the target key. So we won't waste time on that because I already did waste time on it. And after a couple of days, it had pretty exhaustively searched and did not find anything. And so I felt that that was sufficient enough to give up on that. But we're going to go ahead and dig into this program, and we'll be able to kind of figure out what this vulnerability is. So as you can see here in IDA, it drops us into the entry point of the program, and we can go ahead and see these handy little function references here. So we can see it says keygen main. So this is a keygen class and the main function that's being called. So we'll go ahead and click on that. And I won't go too much into detail about the assembly that's happening, but if you're someone who's not that familiar with reverse engineering and looking at assembly like this, there are a few things that you can look at just to make it easy as a beginner to go through. You can look at these function names and you can kind of determine what's about to happen, and then also you can understand that when a function is called in assembly, the preceding lines are going to be pushing the arguments of that function onto the stack. So that means that if you look beforehand and see these registers that are getting values, you can set a breakpoint at a function, and when you run the program, you can stop it at that moment and look and see what the arguments are of that function. So we'll kind of just go through this really fast, and we'll see that these function references say clap, app, new, and a quick Google search reveals that this is a program that is built in the Rust language, and it's using an argument parsing library called clap. So we can look at this, and without having to understand too much of exactly what's happening with the assembly, we can look at it and see that the arguments are being set up with a certain name, has a short name, a long name, the value for the name, it takes a certain value, has a default value, help text. We move on down. So this is basically just where it's setting up the arguments that are expected on the command line. And if we continue on down here, we're going to basically just kind of jump through all of these arguments, and it does a little bit of parsing and loads everything up. And then finally, we're going to get down to kind of the meat of the program here. So if we look at our graph view, we can drag it down here. And we see this function called time keygen generate RSA key. So that seems like a pretty good place to start if we're trying to figure out what the vulnerability is. So we'll go ahead and click here. And if you're not familiar with IDA, then you can jump across this reference here. You can click to the actual function itself. And this looks like a good point to determine sort of what's happening here. So we'll go ahead and set a breakpoint at this jump here so we can see kind of which way the program is going to flow when we run it. You'll get a message saying, be careful to run unauthorized code, make sure you don't get a virus. But we'll go ahead and run this. I'm just going to exit out of a few windows here so we can see a little better the things that matter to us. And so now we've reached this breakpoint, and we can see that the program is about to go that way. So we follow this over here. We can see the program is about to hit another jump there. We can advance it, continue over this way. And now we see this function called select key params. So again, that looks like something that's going to be important, because if there's something that's being used to generate this key, we're going to want to know where it's getting those values from. So we'll go ahead and jump to our next breakpoint. Now at this point, we want to know what's happening in this function. So we can actually click the button here to continue to execute each instruction. So we're actually going to go into this function line by line, and we can see what happens. So we see that it compares a value here. It has 800 hex, and it's comparing that to 200 hex. And so we know that this program is going to generate, if you take time to look at the arguments that are available, it's going to take time to generate a certain key size. So you can put in 512, 1024, or 2048. So that 200 in hex is going to be 512 bytes in decimal. So we can see it's looking at that argument and seeing if we're looking at a 512 key, which we're not, because it defaulted to 2048, which is 800 here. So we can see that the program's going to go over this way. It's going to look and see if we're looking for a 1024-bit, which we're not. So then it's going to jump over here, see if we're looking for an 800 for a 2048, which we are in this case. And so if it failed there, it's going to panic because it doesn't know exactly what value you're actually looking for. And you can see the beginning of this message here for an unsupported key size. So instead, we can see that it's going to continue down here. Now when we get to this Rust allocate pointer here, we can actually, instead of using execute line by line, we can use to execute without entering functions, because we just want to kind of skip over some things. And so now we're coming down here where it's going to be doing some things. Another easy hint that you'll find with IDA, whenever you're doing any kind of capture the flags or anything like that, is that when you see these values here like this UNK, then that's going to be something, a string or some value that it's loading from from inside the program. So a lot of times in CTF competitions, you're going to find either flags or hashes of flags or some value that you can use here. So we can see that it's loading this value. And if we click on it, we see there's a nice long string here. We're looking at it and we see some plus signs. We see some slashes. We see an equal. So we're pretty certain immediately that this is a base 64 string. And we can see that there are a few of them in here. So now, if we want to take notes on this, we'll say that the first thing it does is load key params. And that means that it's going to load a base 64 string. And it also checks to see what the key size is. So we'll continue on down here. And now in this next block here, we see something that's being loaded here. We click on it, we see it's another base 64 string. This is a different one. So we'll say load base 64 string. We'll call these 1 and 2. So now we continue on down. We've loaded that string. It's allocating space for it, putting it in here. And so now we reach another point where it's going to load something. So we look at this, and this is where it gets a little curious because you can immediately recognize that we're loading a public key. And so that's par for the course with a challenge that is dealing primarily with RSA. So we see that it has a full public key here. It's rather long. And if we look further up here, we'll see there are other public keys. And this one's slightly shorter. And then another one that's even shorter. So we can kind of infer at this point that these parameters are going to be based on what size key you select, or what size key you're trying to generate. And so that's going to be kind of a clue to how these are used. So now we know that it's for each key size, it's going to load 2 base 64 strings, and then it's going to load a public key. We'll go ahead and save this. And so now we continue on down here, just kind of moving it around into memory. And now we've pretty much reached the end of that function. So now we know what happens in that select key params. And now we can see where we're moving things around. And we're going to go ahead and jump to this next breakpoint that we've just created and see where it goes. So we're going to move down into this block. And now we see another function here. And this one is actually called gen key. So it looks like we've loaded the parameters into memory, those 3 strings, and now we're actually going to jump into this gen key function. And that's where we're going to actually generate the RSA key. So we'll go ahead and jump down here, and now we're going to dig into this. As you can see from the graph overview, this one has a lot of different moving parts. So we can guess that this is going to be where we're going to find the actual algorithm that we're going to be using to generate this, and likely we're going to be finding the vulnerability behind it. So let's go ahead and look here. And the first things we see this public key from PIM. And so we can assume that we're going to be loading the public key from the public key that was loaded here. So we'll be actually loading the value of that public key. So if we go in our notes here, we can add this. kind of make a note of what's happening. And the important thing is just to keep track at all times what's happening in the execution, so that we can figure out the algorithm that's being used and then find a way to reverse it. So now we've stopped at this breakpoint here. We're going to go ahead and go over this way and follow it. And we can see that it's going to come over this way. And so now we see another interesting function here, get R keys. So we'll go ahead and go into that function and see what's happening. So the first thing we see is we see this base64 decode function. So go ahead and add a breakpoint there. And where it's moving things around here, we can assume that this is going to be the actual value that we're going to be getting, that we're putting into this. This is going to be the argument here. So if we click on this and we just want to verify what this is going to be, then we can look at this these values here. And what you may not recognize right away is that this is actually a memory address. This is going to be a pointer, but the bytes are in reverse order. So you see how these over here kind of match up with it. So if you hit G in IDA, you can go ahead and type this. So say 556C 5546A090. And sure enough, when we go to that address in memory, we find our base64 string. So we can see that what's happening in this function is it's going to be loading this base64 string and decoding it into hex. So we'll continue down this way. And now we see another function, OpenSSL bignum from slice. And so that means that it's going to take some number that was in this base64 string, and it's going to load it as a bignum in the OpenSSL library. So we can tell that we're going to be using those in some arithmetic somewhere. Continuing on down, we see another base64 decode. And at this point, we can kind of guess that that's going to be our other key, our other base64 string that we had. And again, loading it into a bignum. So now we have our two numbers, and we know that they're going to be used in some way for some math, which is a large part of doing RSA in general. So doing a little cleanup, deallocating things, and then we're going to be returning. So now we know that the get R keys function will actually go ahead and decode two base64 strings and save as bignum. So we'll look on down here and we'll see another jump that we can go to. So let's go ahead and set a breakpoint here and then continue this process. So now, continuing on down, we see we're getting the bits of something. It's likely going to be our one of our strings. And now we see a very interesting part, because this is one of the core parts of doing RSA, is that you need to have a prime number. So we can see that it's actually going to generate a prime number and use that in some way. So if we continue on down, it takes a second to do some processing. And if we add to our notes here that we're going to generate a prime number. Okay, so now we've got a prime number, we have our two base64 strings, and the next thing we see here is this function called bn XOR. So we kind of assume that that's going to be a big num XOR function. So if we stop here, we can look at these arguments. These two that are right beforehand are probably going to be the two things that are going to be XORed together. So we click on one of these and follow this pointer. Sometimes these can be a couple layers deep. And now we see some number here. Now this doesn't look like our number for our base64 string. So we're going to guess that this is probably going to be the prime number that was generated in that generate safe prime function. Now we click on this other one. And we come back, and it appears that this is the base64 string that we saw before in hex form, except it's in reverse order. So one thing is the way that the big nums are stored, these will be stored in reverse byte order. So you'll see the first byte down here at the bottom, and then all the way up in reverse order. So now we know that the first thing that's going to happen is that it's going to XOR the prime with string 1, or we'll call it key 1. So continuing on down, we see that it's going to go this way next. And we'll see this function UCMP. And what's happening here actually is that it is going to look at the value of that XORed value, and if it is less than the public key, then it's going to go to the right, otherwise it's going to go the other way. So we see that it's going to continue this way. It looks to see how many bits are in that XOR value. And now we see it's looking to set up a RSA pointer here, and it's looking to see the size of that value from the XOR. And now we see this function, the big num to vector. So this is where it's actually going to take that XOR value and it's going to reverse it and put it in a form that it can do some math with. And so now the next interesting thing that we see here is we see this RSA public encrypt pointer. And what's actually happening here is that you recall that we had a public key that was stored in the program, and so we can assume that it's going to be encrypting something now. If you Google this, you'll see that it actually is a part of the OpenSSL library that you can use to encrypt a value using a given public key. So what's going to happen here is it's actually going to encrypt the XOR value with the public key. And we'll continue on down here and see what happens next. So now it's just kind of doing some cleanup. It loads the output of that public encryption back into a big number object. Okay, and now we see that we're going to be getting that big number back to a vector, free that up, get it back into a big number. So we're basically just kind of doing a little bit of garbage collection here. And it's a lot of clicking, but we're kind of just going through line by line so we can understand what's happening here. Now we're going to be getting down to the next part of this where we have another XOR here. And I won't go into too much detail of digging through what's actually happening here and how you can find this, but if you're following along with the execution of this program, the way that I did it was just to pull up Python and just start writing this out as you go. So what I would do is look at the value that was loaded from the program, those base64 strings, and then as the execution continues, load up the prime number that was found that you see in memory, and then just sort of imitate each of these executions as you go along and make sure that your values from your Python script match up with what's happening here. And so what this ends up happening is that now we're going to take the encrypted value and we're going to XOR it with key 2. So it's going to do a little bit of random things here. Going to move that to a vector. So now we're looking at it in kind of a string form of hex rather than as a big number. Anytime you see this to vector, that's where it's kind of converting it to a hex representation instead of the number object. So now we see another interesting thing here. We see this get rand bytes function. So now we know that we're going to be getting some randomness that we're putting into it. And where those random bytes go, that's where we're going to find out. And so we can see that it gets some random bytes here. And continuing on down, moving some things around, reallocating. And reallocating this pointer could mean that we're increasing the size of it, which actually is the case because the next thing you see down here is this copy from slice function. And if you spend some time digging through these arguments and through the things that are showing up in your registers, what you'll find is happening is that it's actually going to append these random bytes onto the end of our encrypted value that was XORed with key 2. So we'll say we're going to generate random bytes, append random bytes to XOR value. So now we have one big string here that has the first half of it is this XOR value, and the second half of it is a bunch of random bytes. So that's where we're kind of putting some randomness into the program. And then continuing on down, we see that it loads that value into a big num object. When you see this from slice, it's taking the hex representation of the number and actually moving it into an object where it can do math with it. And now we see this arithmetic function here. We see big num, OpenSSL, big num, arithmetic, and this div here. So we're dividing something. And if you look at the arguments that are in here, what's actually happening is that it is going to take that random string. So it'll take long string and it divides it by the original prime number. And then finally, at the bottom here, we get to this thing that says is prime. And so that's going to actually be checking to see if the output from that division is prime. Move some things around. So if the number is not prime, it's going to go over this way and then continue down to this block here. And it says add word. So we have a number 1, and then we have our argument here, which if you look at it is going to be the second of those base 64 strings. So we can see that if it's not prime, add 1 to key 2. And do a little bit of cleanup. And now we see this 3A8 here, and we see a 1. It's comparing our 1 to the 3A8. So 3A8 is actually going to be the number 1000. So if we continue here, we see it jumps all the way back up to the top. So basically what that means is we're going to be doing this loop up to 1000 times. So we have our numbers here. So the point that we're coming in at is up here at the top in this first XOR. So at this point, we can kind of say for I less than 1000, we'll be doing this loop. So what it means is that we're going to be continuing on down through this loop and continuously trying to find a long string like this, that if we divide the prime number, then it comes up with another prime number. Now the interesting thing about this is that this long string that we had our random bytes appended to it, if you recall that RSA is formed by 2 large prime numbers being multiplied together, if we divide the original prime number, we'll call it P, from this long string of values with the random bits attached to it, and we get a prime number, we'll call it Q, then that means that this long string of bytes is actually the public key. And because those 2 numbers multiplied together equals the modulus of the public key. So it means that we've generated a set of random bytes. We've actually taken the original prime number, we've hidden it through this process, and then added some random bytes onto the end so that every key will be different. However, it also means that if we have these 2 base 64 strings, then we can actually go ahead and decrypt the original prime number. So that's basically the entire process of reverse engineering this keygen executable. And in the next video, I'll go into more details about building the exploit that we're going to use to actually crack these RSA keys. But first we can look at some more details of the entire process that I built with this flowchart here. So we can see the original safe prime that's being generated in the beginning, and then it's XORed with the R1 key, and at that point it determines if it's less than or equal to the value of the public key modulus. If it is, then it increments the R1 key by 1 up to 10 times. On the 10th time, it calls a function called permute R keys, where it takes in the R1 key and applies a hash function to it depending on the bit length of the R1 key. So if it's a 256 bit, it applies SHA-256. If it's 512, it applies SHA-512. And if it's 1024, it applies SHA-512, then hashes that output a second time, and then appends the two halves together to create a 1024-bit R1 key. This is how it can ensure that it doesn't get stuck in a loop trying to increment the R1 key, and will eventually find a value that reaches the correct outcome of a prime Q. After it determines the correct value for the R1 key, it continues by encrypting it with the public key and then XORing it again with the R2 key. Then it generates random bytes equal to the bit length of the output of that XOR and appends them to the end of the output to double it. Then it divides the original prime number P from that big number and gets a final output of Q. If the Q number is prime, then we have our two prime factors that are needed to construct the RSA key pair. Otherwise, it increments R2 by 1 and continues the process and tries again. It'll do this up to 1,000 times before it tries again from the very beginning and generates a new prime number. This means that when we decrypt this, we only need to loop up to 1,000 times, because any key that successfully was found is going to be found within 1,000 iterations. So now we'll go ahead and stop here on the reverse engineering part and pick up next in a separate video where we'll explore the actual exploit process.